In this video, we continue our studies of linear algebra with section 1.3 from the Linear Algebra and its Applications text, 3rd edition update by Lay. Okay, so what we're going to talk about in this video is what R is, and what R2 is, and what R3 is, and what Rn is. And then we're going to define a vector and contrast that with the definition of a scalar. And then we're going to talk about equality of vectors. That should probably go up here. And after we talk about what it means for two vectors to be equal, we're going to talk about adding vectors algebraically and geometrically. We're going to talk about scalar multiplication algebraically and geometrically. And then we're going to talk about some conventions used by Lay with this particular textbook. Now, the conventions that Lay uses will be helpful if you're using this textbook as a reference, but they don't necessarily line up with conventions used in other texts. So there will be some differences here between what you have seen or you will see in this video and what you will have seen in, say, my Calculus 3 videos. For example. So we're going to talk about what those conventions are. And it's fine. It's easy to keep clear. You just have to be aware of it. So I'll help you become aware of it. And then we'll list some properties of vectors. And then we'll talk about what a linear combination of vectors is. So that's the plan. Let's get started with a discussion of what R is. R is just the entire real line. That's our notation for the set of real numbers. And that's typically denoted by the interval from negative infinity to infinity. If I wanted to graph this, I typically graph it with a real line, and it's convention to draw the positive x-axis to the right and the negative x-axis to the left. But R represents every point on the real line. It's the entire real line. Now, R2 is the set of ordered pairs where each element in this ordered pair, or each coordinate in this ordered pair, is a real number. Now, geometrically, the way we typically draw R2 is we take an x-axis, that's an entire real line, and we stick with our convention. We'll put the positive x-axis on the right and the negative x-axis on the left, and then we take another axis. We make that perpendicular to that axis, and we line up their 0 points, and we tend to choose to make the positive y-axis going straight up. All of that's relative. It's just a choice. But once we make that choice, we have to stay consistent with it. So this is the xy plane. R2 is a set of all points in the xy plane. Now R3, as you can imagine, rather than being a set of ordered pairs, where each of the values in the ordered pair is a real number, R3 is a set of ordered triples, where all three of those values are real numbers. Now, if I want to graph this, well, I need a third axis that is perpendicular to these two. So typically when we draw this, we try to draw it with a little bit of dimension. We draw it with perspective. I guess I don't want to use dimension in that way. We're talking about linear algebra. So I've got my positive y-axis over here, my positive x-axis over here, my negative x-axis is going back, and my negative y-axis is going that way. This is forming a plane. Then perpendicular to that plane, I want to add a z-axis. So the negative z-axis is below the plane, the positive z-axis is above the plane, and all three of these axes are perpendicular to each other. This is three-dimensional space. And we denote it by R3. Now, if I wanted to draw Rn where n is greater than 3, so n is 4, 5, 6, or so on, I can't draw it in the same way. But it's easy to write down something that's very similar over here for Rn. So where the real line is a set of all real numbers and just consists of a single value, and R2 consists of a set of ordered pairs, and R3 consists of a set of all ordered triples. Rn consists of the set of all ordered n tuples. Once you get beyond 3, we usually start labeling them with subscripts. This is x sub 1 through x sub n, where the x sub 1 through x sub n are real numbers. That's Rn. We think of this as n-dimensional space. Now we can't draw it because we live in three-dimensional space. If I tried to draw an axis that was perpendicular to the x-axis, the y-axis, and the z-axis in three-dimensional space, I couldn't do it. There isn't a fourth dimension for me to draw that axis. If I tried to draw any axis in three-dimensional space, unfortunately, it's going to have components in the x direction, y direction, and z direction. So there's no way for it to be perpendicular to all three of these axes at the same time. But I can imagine doing what we did here, where we went from 1 dimension to 2 dimensions, and then to 3 dimensions, and then we have 4 dimensions and 5 dimensions. We can't visualize it, but we can think of these variables x sub 1 through x sub n as being independent from each other, and in some sense representing perpendicular directions in n-dimensional space, even though we can't visualize it because we're in three-dimensional space. Okay, so that is what Rn is. Now, the definition I'm about to give you for vectors is different than the definition for vectors given in the text. So a scalar is a quantity characterized by a single number. While a vector is a quantity that has magnitude and that's given by a single number. So we can think of a scalar as being characterized by a magnitude only. But a vector is a quantity that has a magnitude and a direction. So scalar quantities, these are quantities characterized by a single number, might include mass, or area, or time, distance. While vectors have magnitude and direction. Quantities that have magnitude and direction. It'd be force. If I'm applying a force, the direction matters. If I give you 50 pounds of force and I'm pulling in one direction, that's very different than applying 50 pounds of force in a different direction. So the direction matters. So that's a vector quantity. Displacement is a vector quantity. Velocity and acceleration and jerk are vector quantities. Let's see over here, scalars, volume. We talk about that. Now these are all characterized by a single number. Vectors have magnitude and direction. When we graph vectors, we tend to graph them with arrows. whoops, arrows, there we go. So the magnitude of the vector is proportional to its length. If we're talking about vectors in an abstract sense, we might use the term magnitude and length interchangeably. If we're just doing math with vectors, we might think of the magnitude and length as exactly the same thing. When we talk about physics, the magnitude of a vector tends to be proportional to its length. I'm not going to, if this represents 50 pounds of force going in this direction, there's not really a way to draw 50 pounds. So the length of the vector can't be 50 pounds, but a 50-pound force might be represented by this, and a 100-pound force in the same direction would be twice as long and pointing that way. So in that way, when we talk about physics applications of vectors, magnitude and length tend to be proportional to each other. And the direction, of course, is indicated by this arrow. It's indicated by the direction that this arrow is going in. Okay, now if we have, so that's how vectors tend to be described in other classes. That's how vectors are described in Calculus 3 and how scalars are described in Calculus 3. They're described a little bit differently in the lay text, though. In the lay text, we're going to talk about column vectors. And in linear algebra, all of our vectors tend to be column vectors. These are matrices that have only one column. So a vector in this linear algebra sense, in the sense used by the author of our textbook, Lay, is going to be written something like this. We'll say that U is a vector. And if it is a vector in n-dimensional space, we would write it this way. So this has n entries. This is an n, it has n rows and one column. So this is an n by 1 column vector. So for example, U equals the vector 1, 3 is a 2 by 1 column vector. So it has 2 rows and 1 column. We might have a vector 1, 2, 3. Well, that has 3 rows and 1 column. So that's a 3 by 1 column vector. Or we might be working on some application where we need more entries to represent more independent variables or values for independent quantities. And so maybe we've got something that looks like this. Well, I've got these 4 numbers on a list, and we are listing them vertically like this. So that has 4 rows and 1 column. So this is a 4 by 1 column vector. And this is our just sort of generic column vector U with components U sub 1 through U sub n. We call those the components of our vector. We call 1 a component of the vector and 3 a component of this vector, and 1, 2, and 3 components of the vector V, and 2, 3, 4, and 5 the components of the vector W. Now, this is the notation used by our textbook author. Now, what Lay says is that rather than thinking of this as a vector that's corresponds to a visual representation like this, So it could be represented by an arrow that starts at the origin and heads out to that point in n-dimensional space. So we'd start over here at 0, 0, 0. And if this is a vector u, we would go to the point u1 through u sub n in n-dimensional space. Now, of course, if n is greater than 3, this is a bit of a cartoon. We can't actually visualize this, but this cartoon helps us to make concrete this abstract idea of n-dimensional space. But we start at the origin, we go out to this point, u sub 1 through u sub n. That's how I would tend to think of this n by 1 column vector, u. This, according to Ley, corresponds to the point u sub 1 through u sub n in n-dimensional space. So when he talks about Rn, he's not talking about the set of all ordered n-tuples, or, well, he is talking about the set of all ordered n-tuples, but he's associating every point in n-dimensional space with a particular vector, rather than thinking of a vector as starting at the origin and pointing to that particular location. It's a little bit different than what we did in Calculus 3. In Calculus 3, we said that these points were different from the vectors that pointed to those locations. But Ley is saying that we're going to use those interchangeably. We're going to think of u as being a value in n-dimensional space. So we're associating this vector u with a point rather than associating it with that arrow that goes from the origin to that point. Similarly, this vector 1, 3, Ley is associating with the point x equals 1, y equals 3. And he's using brackets over here and parentheses over here. He's using a comma here. He's not using a comma here. This is a 2 by 1 column vector. And he's saying it's the same as this particular location in two-dimensional space. Now, again, this is not always used interchangeably. Sometimes we distinguish between vectors and points, but Ley is not distinguishing between vectors and points. He is associating this vector with this point. Now, he does also point out that the vector 1, 3 is not the same as the vector 1, 3 over here. This is a column vector. It has 2 rows and 1 column. This is a row vector. It has 1 row and 2 columns. So these are not equal to each other, but he is saying that this vector 1, 3 corresponds to this point 1, 3. So if I were to draw the vector u in the way that we're accustomed to, I would go to x equals 1, y equals 3. I would plot that point, and u would be the vector, the arrow, if I was trying to visualize it, that starts at the origin and goes to that location. We would say that this arrow or this vector is in standard position because it starts at the origin and then it goes to the point x equals 1, y equals 3. Ley is saying, let's treat 1, 3 and u itself as interchangeable. That's what he's going to do throughout this. And the same is true with this vector 1, 2, 3. Rather than thinking of that vector v in this way, so we're in 3-dimensional space. We go 1 unit in the x direction, 2 units in the y direction, 3 units in the z direction. And I like to draw a little rectangular box, because it's just a box, by drawing lines, dotted lines that are parallel to my axes. So I go 1 unit in the x direction, 2 units in the y direction, 3 units in the z direction. So my vector starts at the origin and goes out here to the point x equals 1, y equals 2, z equals 3. So all of that is true. That's the vector v. Now Lay is saying, let's treat the vector v and the point 1, 2, 3 as interchangeable. Now, I can't visualize this one because I can't draw a fourth linearly independent axis here. I can't draw an axis that is mutually perpendicular to the x-axis, the y-axis, and the z-axis to get that fourth axis for the fifth, or for that fourth component in our vector w. So I can't draw that, but he is saying that let's associate that vector w with the ordered 4-tuple. Sometimes I've heard it called 4-tuple. I call it 4-tuple. 2, 3, 4, 5. Okay, so that is a convention that we're using and that we will stick to. And he is also tending to say that when we have a vector like this, we can visualize it either as a point or as a vector that starts at the origin and goes to that point. Other textbooks will say that it does not necessarily have to start at the origin. So you might say, that leads us to our next idea, the equality of two vectors. What does it mean for two vectors to be equal? We tend to say that two vectors are equal if they have the same magnitude and direction. So the vector u can be written this way. You start at 0, 0, you go 1 unit in the x direction and 3 units in the y direction. This is your vector u. Let's say that P is the point 1, 1, and that Q is the point 4, 2. Question might be, is PQ equal to the vector u? Well, if I want to figure that out, let's sketch that. We'll go to x equals 1, y equals 1. And then we'll go to x equals, oops, I think I did this backwards. I had 1, 3 here, not 3, 1. This one's not going to work. Let's make this 2 and 4. I'll start at the point 1, 1, and then I'll go to x equals 2, y equals 4. And I'll plot that point. That's my vector from P to Q. We call it the vector PQ. Now we can see from this picture, hopefully, that these two vectors have the same magnitude and direction. They're parallel to each other. If I had a perfect grid, you would be able to see even more. It would be even clearer that they're parallel to each other. It looks like U has a little bit of a curve in it. It's not supposed to have a curve. But another way that you can see, well, they're parallel to each other. They seem to have the same length, and they seem to point in the same direction. You could almost pick up PQ and lay it on top of U, and you would see that they are exactly the same. Another way that you can check that the vector PQ and the vector U are the same is by writing the vector PQ in what's called component form. And the way we do that is we take the coordinates of Q. So I'll call that Q1 and Q2 there. And then we subtract the coordinates of P. So in our case, Q1, Q2 is 2, 4. P1 and P2 are both equal to 1. So if we simplify that, 2 minus 1 is 1. 4 minus 1 is 3. We see that PQ is the vector with components 1 and 3, and U is the vector with components 1 and 3. So these two are equal to each other. Now, the author of our textbook, Lay, does not keep this in mind. He doesn't say that this vector is the same as this vector, that you could just take this vector, pick it up, and put it over there, and say that those are the same. He's not using those interchangeably. What he says is this. Lay says that two vectors are equal if and only if their entries are equal. And seeing that we find the entry of the vector from P to Q using this formula, taking the coordinates of Q and subtracting the coordinates of P, we get this. We can see that this vector 1, 3 is the same as this vector with components 1 and 3. The entries are 1 and 3 here, and the entries are 1 and 3 there, so the vectors are equal to each other. So these are two different ways of looking at the same thing. But again, he is still saying that the vector 1, 3 is associated with this location, x equals 1, y equals 3. Whereas this is saying something different. This is saying that wherever you start, you want to go 1 unit in the x direction and 3 units in the y direction. So in general, if we have U, let's say we're in 3-dimensional space, but we could easily be in 2-dimensional space. This vector U tells us to start at a particular location and go U1 units in the x direction, U2 units in the y direction, and U3 units in the z direction. If we do all of that, we're going to end up at Q. So that's a little bit of a different perspective. This perspective that I just talked about is probably more familiar to you. It's what you have done in your physics classes and what you've done in Calculus 3. But Lay is using this term a little differently. He is defining vectors in terms of these components. And he is associating vectors with particular locations. So rather than thinking of this as a point in R2 and this as a vector that goes from some point in R2 to a different point in R2, he's thinking of this vector and this point as interchangeable. So he's saying that this is in R2, this is in R3, and this is in R4 because it has 4 components. But he's associating this with a point in the plane, a point in 3-dimensional space, and a point in what we would call 4-dimensional space. Okay. So we've taken care of this, and we've taken care of the difference between a vector and a scalar. Vectors have magnitude and direction. Scalars are characterized only by magnitude. So area doesn't have a direction. Time, we might think of it as having a direction, but we don't tend to think of it as having a direction. Distance is always non-negative. It's always positive or it's 0. We don't care about which direction we're going. We're measuring a length. It's a magnitude. I guess I should add length to the list. Mass, force, and an application of force or a type of force is weight, mass times gravity. Just for example, that's a vector where mass itself is characterized by a single number and it's magnitude only. It doesn't have any direction at all. So that's the difference between a vector and a scalar, but for our purposes in our study of linear algebra, we're going to use vectors and points in n-dimensional space and to think of those two as interchangeable, because that is the preference of the authors the author of the lay textbook. It's a subtle point, and it really just depends on the context when you're talking about these ideas, but it's good to be comfortable shifting from one perspective to another. It's good to be able to say, okay, well, what do you mean by that term? Okay, well, if that's what you mean by that term, I can get on board with that and still understand what you're saying. It's all about the communication. Okay, so now we're going to talk about adding vectors, both algebraically and geometrically, and scalar multiplication algebraically and geometrically. We've already talked about the equality of vectors. Then we'll list some properties. They're pretty much exactly what you would expect. Associativity, commutativity, distributivity. Then we'll talk about what it means to form a linear combination of vectors. And this is a lot of repetition from the vector videos at the very beginning of my Calculus 3 playlist. But we're adding all this these extra layers of interpretation to be consistent with the author of the lay textbook. Okay, so let's say that you have two vectors and you want to add them. Adding them algebraically is actually really easy. If we have a vector u with n components u sub 1 through u sub n, and a vector v with n components v sub 1 through v sub n, given that, then the vector u plus v just comes from adding component by component. So you take u1 and you add v1, that is your new first component. And then you take u2 and you add v2, that's your new second component. And you keep going. Eventually you have un and vn. You add those together. It's actually very simple. So given these, I guess it doesn't imply that, u plus v is equal to that. So as a quick example, if we have the vector 1, 3, and the vector, let's say -2, 2, these are both in two-dimensional space. The vector u plus v comes from taking this vector u and adding this vector v. All you do is add component by component, and u sub 1 through u sub n are called the components of u. V sub 1 through v sub n are called the components of v. So the components of u are 1 and 3 respectively. The components of v are -2 and 2 respectively. So we just add the first components together. We add the second components together. And we get 1 plus -2, which is -1 and 5. That's the vector u plus v. Now we can also add geometrically, and it turns out that those are going to be equivalent to each other. One of my favorite professors, retired, his name is Larry, Dr. Starhill. That's what he got his Juris Doctorate, and he had everyone call him doctor. He was a very whimsical teacher, and his one of his Larry-isms that I really love is that he'd talk about Mr. Geometry and Mrs. Algebra. He said they have the perfect marriage because they always agree. He said Mr. Geometry is all about the big picture, and Miss Algebra is all about the little details, but they always agree with each other, and they just look at things in a different way. Larry was absolutely right about that, especially when it comes to classes like linear algebra or algebraic geometry or analytic geometry, or just anything that you've studied as far as the relationship between equations and their graphs. That's all about the relationship between algebra and geometry. This can be handled geometrically as well. So there are two different ways to do it. I'm going to teach you how to add using a method called adding tip to tail. And I think this is easiest to think of in terms of displacement. So let's say I'm in Tulsa and I want to go to New York. And on my way to New York, I have a layover in DC. So in terms of displacement, my first displacement is from Tulsa to DC. Then my second displacement is from Tulsa or from DC to New York City. But traveling from Tulsa to DC and then from DC to New York City is the same as traveling on a direct flight from Tulsa to New York City. So if this is the vector u and this is the vector v, this one over here is the vector u plus v. So if I go from here to here and here to here, it's the same as starting here and going over here. I think that's really the easiest way to think about it, because it's intuitively obvious that going from here to here and here to here is the same as going from there to there. But let's make it a slightly more abstract. Instead of talking about displacement, let's just talk about adding vectors in general. If this is my vector u, we call this the tip of u, and we call this the tail of u. So with the tip to tail method, if you're adding vectors u and v, you sketch the tail of v at the tip of u. So if this is u, and my vector v looks something like this, what I do is I take my vector v and I pick it up and I put it over here. I try to draw it with exactly the same magnitude in the direction. Close. So I take it and I put it over here. So this is the tip of u meeting the tail of v. When I take those and I add those together, the vector u plus v yes, I've got went a little crazy with those vectors, little arrows on top. The vector u plus the vector v is the new vector u plus v. It starts at the tail of u and ends at the tip of v. So we start over here and we end over there. Now again, this is easiest to think of in terms of displacement. This is called the tip to tail method. Now the textbook authors don't talk about the tip to tail method, but they talk about what's called the parallelogram method instead. The parallelogram method, is telling us the same thing. So it's saying, okay, let's say you start with a vector u over here, and then you've got this vector v. Try to draw the same vector, approximately like this. And maybe you've drawn them so that their tails are initially at the same place. So maybe we're drawing them in the xy plane. And because we are thinking of these as associated with 2 points, u1 and u2, and v1 and v2, because we're thinking of it this way, and thinking of these vectors as both starting at the origin. And this is what u and v would look like if I was just sketching them in the plane. The textbook authors say with the parallelogram method, u is this point, v is this point, the origin is the third point. The vector u plus v is the fourth point, or the fourth vertex. of the parallelogram formed by the 0 vector, the vector u, and the vector v. Now we have not yet defined the 0 vector. The 0 vector is denoted by that. It's a 0 with a little vector bar over it, and it's just the vector, all of whose entries are 0, and there could be 2 zeros there could be 1 0, there could be 7 zeros. It just depends on where that column vector lives. What does it live in? N-dimensional space, 3-dimensional space, 2-dimensional space? It's going to have, if it lives in n-dimensional space, it'll have n zeros in it. So they're saying this is the 4th vertex in the parallelogram formed by these guys. Or in other words, if I draw the vector v again, just like I did over here, by placing v at the tail of u. I'm trying to do a good job and make it parallel. And then I draw the vector u again. It's the vector from there to there. U plus v starts at the origin and goes out to that 4th point. Now you can also see from the parallelogram method that the vector u plus v, so that's going from here to here and then there to there, and that takes me from there to there, is the same as the vector v plus u. Geometrically it is. Because if I go from here to here and there to there, that's the same as starting here and ending there. So v plus u is equal to u plus v geometrically. And of course, that is always true. Now I'm thinking of this as a sum of 2 vectors, but this is the vector u plus the vector v. It equals a new vector. It's the vector u plus v. That's why it has that arrow over the entire name, u plus v. This is the vector v plus the vector u. When I add those together, I get the vector v plus u. But we can see from this picture, from the parallelogram method, that those are equal to each other. Or in other words, vector addition is called commutative. Now I've just shown you that in the plane, but it's true in n dimensions as well. And commutative just means you can add it in any order you want. So u plus v is the same as v plus u. You can change the order. When you're adding vectors. Now, it may not at all be obvious that that's going to give you the same result as just adding component by component, but actually it does. It gives you exactly the same result, which I think is pretty cool. Mrs. Algebra and Mr. Geometry agree. If I take these guys and I add them together, I get this. That's the same as taking this vector and adding this vector. I'm going to get this vector if I add geometrically. I would prefer to use the tip to tail method here, but let's show that that's true for this particular example, and then we will show that it's true in general, at least in the plane, and then we'll say that it's also true in n dimensions. Now, I think the commutativity property, before we do that u plus v is the same as v plus u is obvious because of the commutativity of addition of real numbers. If if the u sub I, as I goes from 1 through n, are real numbers, and the v's, the v sub 1 through v sub n, are all real numbers, I can add in any order I want. So u sub I plus v sub I is the same as v sub I plus u sub I, so I could switch these. So the vector u plus v has to be equal to the vector v plus u just because of the properties of real numbers. Okay, so let's look at this example geometrically. We want to show that if u is the vector with components 1 and 3, and v is the vector with components -2 and 2, u plus v is the vector with components -1 and 5. We want to show that geometrically this time. So I would start by sketching the vector u. So it has components 1 and 3. If I start at the origin, I'm going to go 1 unit in the x direction, 3 units in the y direction. And then I want to add to this vector u, I want to add tip to tail the vector v. V says to go -2 units in the x direction. And then 1 unit, or then 2 units in the y direction. So we're going back 2 and up 2. That's the vector v. Is that the same as going from the origin to the location x equals -1, y equals 5? It sure is. U plus v is the vector with components 1 plus -2 and 3 plus 2, which is -1, -1, +5. Now, if you prefer, you can use the parallelogram method, which says, here's my vector u, and let's just sketch my vector v. My vector v has coordinates, or excuse me, components -2 and 2. So we get 2 units backwards in the x direction, up 2 units in the y direction. And according to the author of our textbook, the vector u plus v is the 4th vertex in that parallelogram. So u is this point, v is this point, 0, 0 is that original point, and u plus v is the 4th vertex. Well, that's exactly what I would get if I drew a parallelogram where v was over here, and u was over here and here. Now, my parallelogram doesn't look perfect because I didn't really do the spacing quite right over there, and maybe this spacing is not quite the same as that spacing. But if I had drawn a better graph, we could see that this was a parallelogram, and this vector u plus v, or v plus u, whichever way you'd like to look at it, is the vector that goes from there to there. Now, this is what I claim. I claim that if u is the vector with components u1 and u2, and v is the vector with components v1 and v2, u plus v is the vector with components u1 plus v1 and u2 plus v2. And I claim that that is consistent with adding tip to tail. Let's show that it's consistent with adding tip to tail. So let's say I go to u1, u2. So that's my vector u. Now, if I'm adding tip to tail and vector v has component v1, I'm going to go v1 units in the x direction, and then I'm going to go v2 units in the y direction from there. Actually, let's make that a little bit shorter. Maybe that's our vector v. If I'm adding tip to tail, it's like I go from here to here, then I pick up where I left off, I go from there to there. Then u plus v is the vector from there to there. Well, I hope you can see that this purple vector well, the distance, if the distance from here to here is u, or u1, and the distance from here to here is v1, this value for the x coordinate of that terminal point of that vector is u1 plus v1. And if this distance is u2 and this distance is v2, the value for that terminal point in the y direction is u2 plus v2. So I'm taking this u2 and I'm adding that v2 to get my y. And I'm taking this u1 and I'm adding that v1 to get my x. Now, even if v1 and v2 happen to be negative, it's still going to work out in the same way. If one of those was negative, rather than just going forwards, we'd be going backwards. We'd be subtracting instead of adding two positive numbers. But I hope that you can see from this picture that it's the same. the purple vector has components u1 plus v1, as we go u1 plus v1, and u2 plus v2. Okay, so adding tip to tail is the same as adding algebraically, adding component by component. So you can take the algebraic approach, or you can take the geometric approach, and you're going to get the same value. Or if you prefer, you could, with this vector here, you could draw it down here. You could use the parallelogram method as well. Here's u, here's v, here's the origin. U plus v has to be that fourth coordinate, or excuse me, that fourth vertex of that parallelogram. And that v1 is that distance there. This is actually the vector u now. Okay, so this picture is not as clear because of all the little dashes, but I hope that you get the idea. All right, so that is adding vectors. So you add vectors component by component. Or you can add tip to tail. Think of that displacement problem, that layover problem. It makes it really easy to remember how that works. Or if you prefer, you can use the parallelogram method, or parallelogram rule, it's sometimes called. Now, scalar multiplication is similar. The scalars that we will use in linear algebra will all be real numbers, but we could just as easily use complex numbers. We could also use complex numbers for the coordinates here in our vectors u and v. That could be a complex number, and that could be a complex number if we wanted them to be. The same is true over there, but for our purposes, when we're studying linear algebra, we're going to think of them all as real numbers, but remember that everything generalizes to the complex numbers as well. So let's say you have a real number c and some vector u with components u sub 1 through u sub n. Then the vector c times u just comes from taking each of the components of u and multiplying them by c. So we'll have c times u1, c times u2, all the way through c times u sub n. That's scalar multiplication. So if I have the vector, just for example, say I have the vector 2, 3, or 3, 2, because I wrote the 3 down first. Then 2 times that vector is 2 times the vector 3, 2. All you do is take each of these components and you multiply them by 2. And so we get the vector 6, 4. Easy breezy. And that's the algebraic approach to scalar multiplication. You just multiply each component of your vector by that scalar, just like that. Now, the geometric approach, I think, is more interesting. I prefer geometry to the operations here, but I think the connections between the algebra and the geometry are really interesting. When you're talking about the geometric approach, this vector c times u, where c is a real valued scalar, this vector will have the same direction. Well, actually, let's see. It has a magnitude given by the magnitude of, or the absolute value of c times the magnitude of the vector u. And if C is positive, CU points in the direction of U. And if C is negative, CU points in the opposite direction, or the direction opposite of U. Okay, so let me give you a concrete example. With this vector 3, 2, if we multiply it by 2, according to this, the magnitude of C times U, or the magnitude of the new vector is the absolute value of C times U, or the absolute value, the magnitude of C times U is the absolute value of C times the magnitude of U. Now, we haven't talked about how to find the magnitude of U yet, so I guess we need to do that first. So here's our vector U. This is a vector associated with the point 3, 2. If we start at the origin and go 3 units in the x direction and 2 units in the y direction, we end up over there. The magnitude of U is the same as the length of this, this arrow. When we're thinking of this in a geometric sense, magnitude and length are the same thing. Now, when you get to physics, the magnitude of a vector and the length of a vector are not necessarily the same thing. In that case, the magnitude and the length of the vector are just proportional to each other. If I want the length of this, it's denoted that way. In general, if my vector U has components U1 through U sub n, you just take the components, you square them and add them and take the square root. So that's how we find magnitude. So in our case, the magnitude of this is the square root of 3 squared plus 2 squared. 3 squared is 9, 2 squared is 4, so this is the square root of 13. So the length of that vector is square root of 13. So it's square root of 13 units long, where the unit here is measured as the same as the unit over there. So if I want a decimal approximation of that, it's approximately 3.6 units long. Okay, now the vector CU has the same magnitude as that. It's going to be, except you just multiply by the absolute value of C. So if I take U and I multiply it by 2, it's just going to take the same vector and it's going to make it twice as long. That's what this says. I claim that that's exactly the same result that we get if we take the magnitude of this vector that comes from the algebraic approach. So if I take 2 and I multiply by U, I get the vector with components 6 and 4. If I take those and I square them and add them and take the square root, that's the square root of 52, which is 4 times 13. And of course, the square root of 4 is 2. So I end up with 2 times the square root of 13, which is the same thing I would have gotten if I just said that's going to be 2 times the magnitude of U. Okay, so that's the magnitude of that. But again, let's look at this vector geometrically. If I'm looking at the vector 2U now, it should have components 6 and 4. So rather than going 3 units in the x direction and 2 units in the y direction, I'm going to go 6 units in the x direction and 4 units in the y direction. That's my vector 2U. And I hope you can see, if I had done a good job drawing my picture, that this is just twice as long as the vector U. Now, if C is negative, then rather than pointing in the same direction as U, C times U will point in the opposite direction. So let's say I take u and I multiply it by the by the scalar -1/2. So it's going to be -1/2 of 3, or -1.5, and -1/2 of +2. That's going to give me a -1. So I go, if I draw this out over here, that's 1, that's 2. I go -1.5 units in the x direction, -1 unit in the y direction, and that is the vector -1/2 u. So notice that u, 2u, -1/2 u, they're all parallel to each other. They all lie on exactly the same line. If I multiply u by a positive number, basically what that's going to do is it's going to rescale it. If I multiply it by 2, it's making it twice as long. If I multiply it by 3, it would make it 3 times as long. If I multiply it by 1/2, it's going to make it half as long. If I multiply it by 5, it's going to be 5 times as long. So you get the idea. Now, if I take that and I multiply u by -1 or -2 or -5, that's just going to flip it 180 degrees. So instead of being in this direction, it's going to point in the opposite direction. But again, the length is going to be the same as the length of u times the absolute value of that scalar. So -5 times u goes in the opposite direction. It's 5 times as long. It's going to, well, actually, let's think about 5 times u. It's going to be like this. So there's u, there's 2u, you say 3u, then 4u, and then 5u, something like that, approximately. That would be 5u from there to there, approximately. -5u is going to start there and go like way down here. I hope you understand what that means. It's going to be just 5 times as long, but in the opposite direction. So that's what this says. The algebraic approach is really simple. You just distribute. You distribute the scalar to each component and you multiply. Whether that scalar is positive or negative, that's what you do. But the geometric approach, I think, is more interesting. This is saying when you multiply a vector by a scalar, what you're actually doing is you're rescaling something in some sense. You're making it absolute value of c times as long. So 2 times as long, or 3 times as long, 5 times as long, 1/2 as long. And then if you're multiplying by a positive number, you're going the same direction that you were going. If you multiply by a negative number, you're going the opposite direction from where you were going. And that's exactly the same result that you get when you just distribute that scalar to each of the components and with the algebraic approach. So again, Mr. Geometry and Mrs. Algebra agree. They always agree. And I think that that's a very beautiful thing. I lost Larry's phone number after he retired and had some security issues with my phone. So unfortunately, I can't call up Larry and tell him thank you. If anybody knows Larry Starhill, please send me an email. And I would love to reconnect with Larry because he was just whimsical and kind, and he made people love math. And he gave us these beautiful ideas, like the Mr. Algebra or Mr. Geometry and Mrs. Algebra marriage. That was just fun to think about and consistent with the mathematics. So I miss Larry. I believe he's still around. But that's how we add vectors. We add tip to tail, or we add component by component. When we're multiplying by scalars, we multiply component by component, and geometrically, we're resizing that vector. And if we're multiplying by a negative scalar, we flip it. Okay. And then because of what we saw with our tip to tail method and the parallelogram method, we saw at least one of our properties of vectors. I'd like to list the other properties that are listed in the lay linear algebra text for you now. So again, our textbook authors are associating vectors with points in n-dimensional space. So they're not distinguishing between points and the vectors that point from the origin to a particular location. So with that in mind, they say for vectors u, v, and w in n-dimensional space and scalars c and d, and we're just going to stay in R, and this is a real n-dimensional space, the following is true. You can take u plus v, and you can take v plus u. You're still going to end up with a vector, and you can change the order. U plus v is the same as v plus u. This is the commutative property. Commutative means you can add in any order you want. Or commutative property of multiplication would be you can multiply in any order you want. We haven't talked about multiplication of vectors yet. Okay. Now we've got an associative property. Associativity is about grouping. You can group these two guys together, or you can group these two guys together. I want to put little arrows over all of these so that we know that we're talking about vectors and not scalars. This says that u plus v plus w is the same as u plus v plus w. Call that the associative property. And this next one is called the additive identity. There's a vector out there called the zero vector. If you add that to u, if you do u plus the zero vector, you do the zero vector plus u, you always get u back. And then we've got something that's called the additive inverse. If you take u and you add it to the opposite of u, or you take the opposite of u and you add it to u, you get the zero vector back. And this is where negative u is defined to be the scalar -1 times the vector u. And this is called the additive inverse. In terms of displacement, I think of this as being able to undo that displacement. It's like if I go from Tulsa to DC and then I go from DC back to Tulsa, I'm still in Tulsa. I'm thinking of that, the displacement, if I took that round trip, there was no displacement at all. I account for both legs of the trip. So that's the additive inverse. Then we've got scalar multiplication, distributes over addition. So if you have a scalar times a sum of two vectors, you can take each of those vectors and multiply by the scalar and add them together. So you can distribute that scalar. So that's a distributive property. You got another distributive property. If you've got a sum of two scalars times a vector, you can distribute that vector to both of those scalars. So this is c times u plus d times u. And then we've got another distributive property, c times d times u. This is saying take a vector, multiply it by a scalar d. So it's d times as long, and maybe pointing in the opposite direction. If you do that, and then you multiply that by a vector c, that's the same as taking c and d and multiplying those together, getting a new scalar and multiplying that by the vector u. Totally fine. And of course, there is a 1 out there, a scalar 1, so that you can take u and you can multiply it by 1 and you get itself back. That's called a multiplicative identity, but it's a scalar multiplicative identity. And I guess this is a regrouping. So this is a form of an associative property. Associative properties are about regrouping, and commutative properties are about changing the order. And additive identities that just means that there is some number out there in your set, it's usually called 0, that you can add to the other numbers and get the original thing that you started with back. In this case, we're talking about vectors. We take a vector and add it to the 0 vector, we get the original vector back, and vice versa. And additive inverse just means that there's another vector out there that you can add to a given vector and you can get the 0 vector back. So the inverse part is the ability to undo something that you've already done. Okay, so with that in mind, because we have this idea of the additive inverse, we can talk about subtraction. And if you've ever, I'm sure you guys have learned about subtraction of real numbers. Subtraction is the same as adding the opposite. So when I take u and I subtract v, that's the same as taking v and adding negative v, or taking u and adding negative v. Just like when we said, 5 minus 3 is the same as 5 and adding negative 3. Or if we have negative 3 minus 7, that's the same as taking negative 3 and adding negative 7. Every time you're subtracting something, you're adding the opposite. And then we go on from there. The same is true for vectors. Because the additive inverse exists, because this negative u exists for any u, subtracting v from something is the same as adding the negative of v. Okay, so now let's talk about linear combinations of vectors. When we talk about a linear combination of vectors or functions, what we're saying is, we're talking about a new vector or a new function that comes from taking some other vectors or other functions, multiplying them by constants and adding them together. That's all linear combination is. So in the context of vectors, let's say we're given vectors v sub 1 through v sub p, and these are in n-dimensional space. And we've got some scalars, c sub 1 through c sub p. And we're going to treat these as real numbers, although they could be complex numbers. Then we say that y equals c1 times v1 plus c2 times v2 plus c3 times v3, all the way through c sub p times v sub p, is a linear combination of v sub 1 through v sub p. And the weights given to each of those vectors are the constants that are multiplying them. This is kind of like a recipe. You take a little bit of this and a little bit of that. You have C1 of V1, and then you've got C2 of V2, and then you're going to add those together. Then you want C3 of V3, and then you're going to add those together. And we want C sub P of V sub P, and you add all of those together. And then you have this beautiful salad when you're done. So you're taking a little bit of everything, and then you add them together, and you're calling that this new thing. This new thing is a linear combination of the original vectors V sub 1 through V sub P. So let's look at an example. Let's say we have a vector u with components 3 and 2, and a vector v with components -1 and 2. And let's draw those. So we go 3 units in the x direction, then 2 units in the y direction to get the terminal point of u. So there's u. And then if I go 3 units in the x direction again, and 2 units in the y direction again, I end up over here. It's not quite to scale. That's supposed to be 2u. That's a u, and that's supposed to be another u, and u plus u is supposed to be 2u. My picture's not too good. Okay. And the vector v, if we want to just sketch that by itself, we go -1 unit in the x direction, +2 units in the y direction. So there's v. And if I want to sketch 2v, I would go -1 unit in the x direction again and go up 2 units in the y direction again. It should have been parallel. So that's another v, and then together that's 2v. I'm sorry, these pictures are not so good tonight. It's okay. All right. What does Bob Ross say about that? This is from my fridge. It says, ever make mistakes in life? Let's make them birds. Yeah, they're birds now. Can't really make that into a bird. But yeah, that's how I'm feeling at this moment. We make mistakes, and that's okay. It's part of doing math. It's part of drawing pictures. I'm not a painter, but if I were a painter, the idea of making mistakes while painting definitely resonates for me. But you have the idea here. So this is 2u, or this is u, that's 2u, 3u would be like this, 4u would be like that, negative u would be over here, negative 2u would be behind it, and so on. So that's v, and 2v, 3v would be 3 times as long going out to there, negative v would go this way, and so on. So if I want a linear combination of this, let's say that w is 2u plus v. So the weights here are 2 and an implied 1. It's like I've got 2 of the u's and I'm adding 1 of the v's. The way I would find w is I would go to u, I would draw u, and then I would draw it twice, so I have 2u, and then I would add tip to tail. So I would start here at x equals 6, y equals 4, and I would go negative 1 unit in the x direction and positive 2 units in the y direction. To there. So that's the vector v. And the vector w goes from here out to there. So w is a linear combination of u and v. Now sometimes, our textbook author does a beautiful job of this. You can think of the entire plane as being constructed of these linear combinations of u and v. So this is 1u, this is 2u, then we'd have 3u. Then we can go backwards and we'll have, we'd have to go, if the opposite of u would be negative 3, negative 2, so we go backwards 3 units in the x direction and down 2 units in the y direction. That's negative u, and then we could do that again. But we could just keep drawing all of these vectors, and then negative v, we would go positive 1 unit in the x direction, and then negative 2 units in the y direction, and then keep going, and then keep going. We could draw an entire grid, and instead of focusing on our x-axis and our y-axis, we could focus on a line that's parallel to u and a line that is parallel to v. Now, it almost looks like these are perpendicular to each other because my graph isn't perfect, but the vectors u and v, turns out they're not perpendicular to each other. But you can see that if you do this, every single point in the xy plane can be represented as a combination of u and v. So let's say I want to get to, let's see. Let's say I want to get to this location over here. You might say, how do you get to that location? Well, I don't even know what that constant would have to be, but if I go this number of units in the u direction and then this number of units parallel to that v direction, then I would end up at this location. And it looks like that location is x equals 6, y equals, it looks like 3.5, or 3/2, excuse me, 1.5. You might say, how do you get 6 and 1.5 there? Well, it looks like I'm going to take u and I'm going to multiply it by some constant. That constant is between 1 and 2. And then I have to take v and I have to multiply it by a negative constant because v is over here, but I would multiply it by a negative, and it looks like it might even just be negative v. So I'd have some constant times u plus negative v, and that would get me to this location, 6 and 1.5. So every point in the plane can now be thought of in terms of these vectors u and v, because I can say, well, if I'm trying to get here, how many units in the u direction would I have to go to get to that location? And then how many units in the v direction would I have to go? It's like you're taking that layover again, but instead of going from one location to another and to another, like I was talking about with Tulsa to DC to New York City, instead what we're doing is we're choosing to stay on a path parallel to u, and we're choosing to stay on a path parallel to v. And we're saying, if I go on a path parallel to u, I go this many units in the direction parallel to u, and then I go this many units in the direction parallel to v, and I add those together, I can end up here. But that's true for every location. Let's think about this one, x equals 2, y equals 4. You might say, how do I get there? Well, if I want to get there, I would have to go this far in the direction of u, and then this far in the direction of v. So it looks like it might just be u plus v that would get me over there at that location. What is u plus v? Yes, actually that is u plus v. U plus v comes from adding component by component. So I end up at x equals 2, y equals 4. So I go u units, or I go from the origin down to the terminal point of u, and then I go from that location, I take the vector v from here to here. So I go backward 1 unit in the x direction and up 2 units in the y direction, and that lands me at the location x equals 2, y equals 4. So every point in the plane, that point, any point over here can be thought of as a combination of u and v, but you have to have the right recipe, or in other words, you have to have the right weights. The C1 and C2 have to be chosen just right so that you can get to that location or to that location. So that is what a linear combination is. Sorry that my picture wasn't a little bit better. Maybe next time I'll draw a better picture. But think of it in 2 ways. Algebraically, you're just taking the vectors that you started with, you're multiplying them by constants and adding them together, and that's giving you this new vector. Geometrically, taking a vector and multiplying by a constant is the same as rescaling it, or possibly flipping it and rescaling it. So when you're talking about finding a vector that is a linear combination of these 2 vectors, you're saying, I'm going to take this vector, I'm going to multiply it by a scalar, and then I'm going to take this vector and I'm going to multiply it by a scalar, and I'm going to add them together, and I'm going to end up at this new location. And that's what this vector y is representing. It's that new location, or the vector that starts at the origin and points to that location. And that's what this vector w represents. The vector w, that in our case says go 2 units, or go from the origin, and then you want to go from there and you want to go on the vector 2u. So it's like you're going 2 units in the u direction, if that makes sense. But you're going in the direction of u twice. And then you're going to pick up where you left off and then go in the direction of v once. And then they say, where do you end up? Well, that's w. We're thinking of that location as w, because that's what the authors of our textbook want us to do. They want us to think of points in the plane and vectors as interchangeable. Or you can think of vector as the w that starts at the origin and points to that location. Same thing. If you add that vector to that vector, tip to tail, you're getting the vector w. But I think this is a key fact, that if I want to get to any point in the xy plane, I can take these vectors to get to that point. I'd say, how on earth will I get to this point, Miss Townsend? Well, looks like I'd have to go this far in the u direction and then that far in the v direction. U times some constant plus v times some negative constant, because it's going the opposite direction of v, would get me to that location x equals 4, y equals 0. You might say, what about that point? What about this point over here? Well, let's see. I'd have to go some number of units in the u direction. It's going to go in the opposite direction of u. Looks like it's less than, it's a fraction of u because u is that long. It's less than a full u. And then we want to go in the opposite direction of v. So it's going to be a negative scalar times u plus a negative scalar times v, also a fraction. And that would get me to this location x equals -1, y equals -2. And we keep going and we keep going all the way around the plane. every point in the plane can be found this way. And we'll talk more about that next time. So we have talked about properties of vectors, linear combinations of vectors, what it means for vectors to be equal to each other. We talked about adding vectors algebraically and geometrically, multiplying them by scalars algebraically and geometrically. We talked about the difference between a vector and a scalar and n-dimensional space, and how Ley is saying that n-dimensional space, or points in the n-dimensional space, and vectors in n-dimensional space will be discussed as interchangeable. One more thing before we move on. Given the convention used by Ley that we're using points and vectors as interchangeable, we're thinking of vectors as living in n-dimensional space. They're saying this vector u1, u2 corresponds to this location u1, u2. And he says sometimes we draw it as a vector, like an arrow that goes from the origin to that location. So we tended to think of u in terms of this arrow. Ley is saying this point and that column vector are interchangeable. We're thinking of them both as representing points in the xy plane. But sometimes we're actually starting at the origin and pointing to that location, pointing to that point. And I think I said this earlier, but I just want to make another point. These two are not the same thing. Notice the comma here and the parentheses here. This is an ordered pair, and it corresponds to a vector. This is a vector with 2 rows and 1 column, and it corresponds to a point in 2-dimensional space, or a point in the plane. This is a vector with 2 rows and 1 column. This is a vector with 1 row and 2 columns. Those are not the same thing. Those are not interchangeable. This is not the same as that. This is a row vector, this is a column vector, and our column vectors are being associated with points. Our column vectors are not being associated with what's called the transpose, the corresponding row vector. Those are not the same at all. So make sure that you know that the row vector and the column vector are not identical, but our textbook author is saying that this column vector and that point are identical. We're choosing to think of those as the same thing as we read the Ley linear algebra text. And so I will see you next time, and we will talk more about linear combinations of vectors. We're going to talk about what the span of vectors is. We'll talk about the relationship between spans of vectors and linear combinations of vectors and systems of equations, and what we've already studied. And we'll talk about geometric descriptions of this span and the span of 2 vectors that are not parallel to each other. And that will be next time. See you then.